So I'm also going to talk about paradox and contradiction. So another problem with sentence logic comes from certain kinds of statements. So imagine a male barber who shaves all men who do not shave themselves. Does this barber shave himself? I've capitalized shave here. So presumably we mean a simple statement like, the barber shaves himself. If he does, then he doesn't. Because he only shaves the people who don't shave themselves. So if he does, he doesn't. And if he doesn't, then he does. So if we want to if we think this is a grammatically correct sentence that means something, then we wind up with this weird situation. Where if he does, then he doesn't, and if he doesn't, then he does. Now you might think this is just a silly example with words, but this manifested itself pretty devastatingly in the history of mathematics when Frege was building set theory and came up with what he was at that time was calling, well, it was later became called naive set theory, and Russell proposed a similar problem to it, which just said, consider a set that contains, it's a set of sets, so it contains other sets. If you're familiar with set theory in math, sets just contain objects. Sets can be sets. Sets can be elements of sets. And so Russell just said, let's consider the set that contains all sets that don't contain themselves, that are not elements of themselves. And so you get the same problem. Is R a member of itself? Is R an element of R? Suppose it is. Since R contains all sets which are not members of themselves, then R must not be a member of itself. But if it's not a member of itself, then according to our definition, it is. And so again, R is an element of R implies that it's not the case that R is an element of R. And if it's not the case that R is an element of R, then it must be the case that R is an element of R.
So you're just giving R different, like, two identities, basically?
No, R's got the same identity. It just generates contradictory set membership of itself. So another example, moving away from math again. Yeah.
Could you go back and explain how not an element?
Explain what?
Like what R equals like the bracket X.
Oh, so this is just set notation, and this just says R is a set whose members are not elements of themselves. So its members are such that they are not elements of themselves. Now, because we're talking about elementhood, that means they're sets we're talking about, because something is only can only be an element of something if that thing is a set. So we're just saying it contains all those things that are not elements of themselves. Don't worry too much about this. If you've never seen set theory before, don't worry. I'm just going to make a point here about contradiction. So this is maybe a more simple example. A, where A is a simple statement that says this sentence is false, or A is false. If it's false, it must be true. And if it's true, it must be false. So I think this is a true statement, then it must be a false statement. And if it's a false statement, it must be a true statement. So in all these examples, it seems like the truth of it implies the falsity of it, and the falsity of it implies the truth of it. And so P arrow not P, because both of these conjuncts are true, is true if and only if P is false or not P is true, which means it has to be false. And similarly, not P implies P is true if and only if not P is false, or P is true, which means it must be true. And so we get to the real devastating result here, P and not P. So contradiction. But what's so bad about contradiction? There was a proof discovered by the medievals. This actually can be a useful proof if you understand it. And we're going to actually make use of an implicit property of contradictions later when we learn reductio ad absurdum. But consider this proof. Suppose I start with a contradiction. A and not A. Or from the previous example, whatever. Russell said is a member of itself and it's not. Or the liar paradox is true and the liar paradox is false. Whatever you like. Any contradiction. So what can I do to this?
Simplify.
Simplify. And now I know I can disjoin a true statement with any other statement. So I'm just going to add a statement. Because I know A is true, I know A or B, where B is anything I like. But I also know not A. I can simplify again. And so now what can I do?
You can say it's B.
B. And so here's my proof. I started with a contradiction and I proved B. But what's devastating about this is B is any statement whatsoever. Anything I want. If I know that the Russell set is a member of itself and the Russell set is not a member of itself, then I can disjoin, once I've simplified, Brad is the greatest human being to ever live, and therefore I proved Brad is the greatest human being to ever live. Anything I want, including another contradiction. Okay, so given a liar sentence or any contradiction, our logic will prove anything and everything. And this is called ex falso quod limit, which is from the Latin. From falsehood, anything follows. Or for our purposes, from contradiction, anything follows. Yes.
So is this a valid argument?
Yeah, totally valid argument. It uses our inference rules. Absolutely. If you know a true contradiction, you can prove anything.
Is it sound though? It's like how?
Well, that's a good question. Is it sound? Do you think there are true contradictions?
Maybe like quantum physics.
Maybe in quantum physics, right? So anyway, so for now, this is known as the principle of explosion, this idea that we generate any truth we want if we start with a contradiction. But the philosophical question becomes then, are there true contradictions? And if there are, something's going to change in our logic, because our logic can't just prove everything from them. So the question is, how do we deal with this? The first approach is just to say, there can be no contradictions. This is what happened with set theory. Frege invented set theory, Russell derived the Russell set. Frege was devastated by this, but then later ZFC set theory, which is Zermelo-Fraenkel set theory. This, if you're in math, is the set theory you learned today. Doesn't allow the construction of the Russell set. Similarly, there could be no such barber. The barber makes no sense. There couldn't be that barber. Or there can be no meaningful liar sentence. Still, some people think there are true contradictions, and they could even be quite ordinary. Yeah?
So would this be also like not sound and also be valid?
Well, it would be valid.
Okay, it's still be valid.
Yeah, ex falso quod limit is completely valid given the rules we have. It's just, if you don't think there are true contradictions, it couldn't possibly be sound, because there couldn't be a true contradiction. But probably the world's most famous living logician today, Graham Priest, is a big advocate of true contradictions and thinks that they're pretty ordinary, like a transition between two states. You know, if I'm standing here and then I'm now standing here, Priest would argue at some point I'm going to be in a transitional state. Or a better example might be if I'm walking out of the door, out of the lecture hall. At some point, I'm going to be in the lecture hall and out the lecture hall at the same time. Or even other examples might be an ordinary Sorites paradox, so like a heap. I throw a grain of sand on the ground, is that a heap? No. If I throw a second grain of sand on the ground, is that a heap? No. I keep throwing grains of sand on the ground. At some point, it's going to be a heap. But somewhere along the way, we're going to be in this vague state, where it is and it isn't, in some sense. Now, if you ascribe to this solution, where we just say no contradictions, we would say, no, we're going to have an arbitrary cutoff point, where it becomes a heap. And before that, it's not. But maybe we want it to be the case that there are true contradictions, where we say it is and it isn't. Yeah?
It's kind of like if you're like standing on a border, like you're in Ontario and you're in Quebec, but if you're in Quebec, then you can't be in Ontario.
Right. And you know, and then the more crazy examples are things like quantum physics. We think wave hood and particle hood are mutually exclusive properties, and yet we have some superposition or whatever of wave and particle or whatever. True contradiction. But again, you will find all sorts of people who will say no, there are no true contradictions. Yeah.
Could we apply something like this with like Schrodinger's cat?
Well, I mean, if you think that there are true contradictions like that, like the cat's dead and the cat's alive, in the Schrodinger's cat example, then something's got to give in the logic. You can't have the same inference rules. Otherwise, we then just generate every truth. And there are such logics. There are paraconsistent logics that have different difference rules that don't let you conclude anything from a true contradiction. But anyway, just like in the case of strict implication, sentence logic is unable to deal with those ideas. For us, and for the logic we're learning, sentence logic cannot allow true contradiction. We might have it as a premise, or we might have it follow, but the idea is a true contradiction will generate every truth. Okay, that's it for today.